Hello, everyone. Good morning and good afternoon or good evening for those of you who are joining us from Europe or Asia. My name is Rasul Sorkabi from the University of Utah. This is our first session in the forum Earth Science New Map. So let me say a few words about this forum. As geoscientists, we all know how important Earth science is for society, for supplying mineral and energy resources, for the environment, and so forth. However, Earth science is now facing many challenges, ranging from education, employment, funding, to breakthrough discoveries, public relations, policy issues, and so forth. Some of these challenges and issues are related to the 2020 pandemic, but some are specific to Earth science. So we need to discuss these issues and these challenges. We need to take a step back and look at all the progress our science has made and share it with the public and the policymakers. We also need to create new opportunities and new prospects for our research and education and for our community, and how best we can train the next generation of geoscientists. So this forum, Earth Science New Map, is a small attempt in this direction to remap the future of geoscience. And I hope that many geoscientists and especially students join this forum as well. Our speaker today is Dr. Marjorie Chan. She is the Distinguished Professor of Geology at the University of Utah. She has led an active research program in sedimentology and stratigraphy, and in this way she has trained many students. She has also pioneered the study of how Utah's red sandstone country provides a very easily accessible and inexpensive opportunity to study Martian geology and the Martian landscape. For her work, Dr. Chan has received several awards, including GSA's 2020 Distinguished Service Award and GSA's 2019 Sedimentary Division SLOS Award for Lifetime Achievements in Sedimentary Geology, and also the 2018 Hintze Award for Outstanding Contributions from the Utah Geological Association. As a former chairperson of the Department of Geology and Geophysics, Dr. Chan played a leading role in securing funds for construction of the new G&G building at the University of Utah, which is indeed one of the most beautiful geology department buildings in the world. She was also GSA's 2014 Distinguished International Lecturer, for which she gave dozens of lectures in 6 countries in Asia and Australia. I can go on and on, but for the sake of time, I have to be brief. For more information, please visit the website of Department of Geology and Geophysics at the University of Utah. Thank you very much for joining. Now, without delay, I would like to hand over this meeting and the screen to Dr. Marjorie Chan to deliver her presentation entitled Geoconservation, Preserving Our Heritage and Opportunities for the Future.
Thank you for the kind introduction. I'm happy to be able to discuss geoconservation today and some of the topics on preserving our heritage and the opportunities there might exist for the future. My talk will be composed of 3 different parts. First, I'll talk about rock archives and some of the ethics that we would use. Number 2, I'll talk about the case of the missing marbles. And the third aspect I'll talk about is technology and where things might go in the future. We're very fortunate to work in remarkable places. As geologists, we get to see some really spectacular scenery, and how many other occupations really get to call this work? Because we have this strong connection to the landscape, it should inspire us to be concerned about the aspects of geoheritage. In particular, geoheritage means the significant sites of scientific, aesthetic, and cultural value. And this includes diversity at all kinds of scales. So you might think of this as being similar to biodiversity. This includes geodiversity, all the sites that might be important for us to understand more about the world around us. Geoconservation has to do with the idea of preserving sites and conserving. The topic of geoheritage has been very popular and has really grown to a global movement. Almost everywhere except in the United States, where we do have our own national and state and local park system, but those park systems are good, although they can't cover everything. So there might be a road cut or some other significant site that has strong scientific value, but still is not a designated park. Now I'm going to talk about rock archives, and by rock archives I mean some of the best outcrops for science, the pristine ones. And we love pristine outcrops, whether it's on Earth or even on another planet like Mars. And these outcrops are key to helping us make science discoveries. And we need some of these archives for some of the future scientists that might be able to use new tools and approaches. But some of the pressures are increasing, and there are more lawsuits with loss of access, and we see that the humans have altered the landscape. So in some ways, we don't get to access the outcrops or these archives that we used to do so easily. A classic example of a rock archive is the Moab Fault, where there are some spectacular exposures. Here you can see the Cretaceous Cedar Mountain juxtaposed against the Jurassic Entrada. So footwall on the left, hanging wall on the right. And this is located in southeastern Utah. People come here to look at the near 100% exposure of deformation bands that are in the footwall. Students can actually measure and plot deformation band densities and discuss some of the relationships to fluid flow. But what has happened is that in the zeal for perhaps looking at some of these spectacular areas, there has been vandalism. And the Bureau of Land Management actually documented this particular example. They could figure out about what date it was, and they know that this work was done without a permit. This particular picture was actually taken a little bit after the event happened, maybe a year or so. And you can see that even with the passage of some time, these kinds of scars are fairly permanent in our lifetime, and it's hard to make these things disappear. It's really unfortunate because it mars the landscape and the outcrop exposure for future students that come to study that area. In the book Cliffs of Utah, there are classic exposures of deltas and shoreline deposits of the Western Interior Seaway. And this location here in Tusher Canyon is considered one of the most classic examples of hummocky cross stratification. However, somebody went in and actually drilled holes throughout this whole outcrop face, perhaps to look at porosity or permeability. And what happens is that students that want to visit that outcrop later are unhappy with their predecessors and the people that came before and essentially destroyed the view. Unhappy students. Even unsightly drill holes really mar the vertical exposure, and you can see again examples of hummocky cross stratification, but it is really detracted from because of all of these drill holes. They attempted some remediation to fill the holes, but it was not satisfactory. You can see that it doesn't really match, and I don't know that there's really any good reason to have holes that closely spaced for sedimentary studies. Even permanent section markers such as these here, numbers written on the outcrop, affect our ability to photograph pristine types of structures. Here's another example of geovandalism. At a highly visited dinosaur track site, someone went in and took 1-inch core samples within the single Jurassic footprint that's outlined here in yellow. Again, this was done without a permit, and it's really unfortunate for those that want to visit afterwards. Here's an example of a scarred archaeological site where there were petroglyphs along a well-used BLM trail. Here you can see some of the holes, probably for paleomag, and these samples could have very easily been taken on the back side of the outcrop where nobody would see it, but it's right along the trail. The excuse was, well, we didn't see any petroglyphs. But when you're taking holes and samples like this, it's hard to imagine that you could even possibly miss these kinds of petroglyphs in this Miocene tuff. In other examples, you might think you're in an isolated area here in Pleistocene-linked Lahontan deposits. Here is a tufa tower that had naturally toppled over to reveal all this wonderful stratigraphy, all these different generations of the tufa. Yet somebody came in and did some sampling across this and didn't bother to remediate it. Even here with this lovely example in this outer exterior surface of this upright tufa, these holes, again, these sampling holes really mar the exposure. So as a practice, geologists should probably have a little baggie of quickset cement. We've already got our water bottles. We don't even probably need mixers. We could just probably mix it up in the bag. And we should probably try to remediate sites, whether or not we've done the damage or not. And at a minimum, we should mix in some local rock. So here's some examples of the drill hole sites. And what you could do is mix your cement with some of the local rock, fill it in, and it would look like this, which is much more palatable and at least is not as glaring. Here are some examples of Miocene evaporite deposits in southeastern Spain, the Sorbis Basin. This is a classic locality that people come to look at these exposures of the evaporites along this riverbed. And because so many people visit this, it would really be best not to mar this or not to make marks on this. Yet there might be busloads of students that all have brand new rock hammers and they want to try them out on these evaporites. But the evaporites are so hard that you really can't even knock off a sample. And so what ends up happening is that you have all these marks. And again, you can't really take a good picture without showing what all those rock hammer hits are. And here you can see a close-up view. So about half of those marks are from hammers. And I think the bottom line is if we have a rock hammer in our hand, we're going to have a tendency to hit. It's just sort of a natural reaction. In this example of garnet pyroxene and a peridotite of Western Norway, here's a classic example of some localities that are here. It seems rather isolated, but in 1978, this particular exposure looked like this. And of course, these are areas that have high concentration of some nice garnet crystals. And even 20 years later, you could see how much more people had actually dug in to extract some of those garnets. And we can only imagine what it might look like now in 2020. Sometimes we're in these areas that might have signs saying protected area. Yet if we're carrying these rock hammers, excuse me, it can really raise questions about whether we're protecting those sites. At the KT boundary in Spain, the layer over time has become progressively indented, in part to people actually digging into the soft clayey layer in order to get samples for scientific study. But is everybody getting those samples for scientific study? You know, maybe we all want a piece of the KT boundary, but what it means is it's getting more and more inaccessible. And here's a geologist that's having a hard time even putting the finger on the boundary. In the Red Rock Conservation Area of Las Vegas, Nevada, you can see some examples here of some beautiful exposures of the Jurassic Aztec sandstone. And if you take a close look at one locality, you can see that it has this funny looking texture on it. And here's a student that was studying this area. And if you take a closer look, what is this? It looks like gum. People have literally taken gum and stuck it on the outcrop. On some of this cross-bedded part and on some of the bedding, the lamina layers that you can see here. And if this were an important site, you might be very upset to have it covered by all of this kind of extraneous material that detracts from the outcrop exposure. So the bottom line ethics is that we should act responsibly. We should leave no trace. These kinds of materials are not biodegradable. We should have minimal impact, and we should remediate sites whenever possible. You know, here is a case where there was a beautiful river in the Alps, and somebody that probably only needed a hand sample took out this whole area and left this damage. So we need to understand and follow all the land use rules, because what we do might actually affect whether somebody in the future might be allowed on the land. And we need to teach etiquette in this kind of sampling here, as well as safety precautions. We should hold high ethical standards, and then that will allow us to preserve some of these localities for future generations to do the same kind of science, or perhaps even more. Data archives might include some high resolution imagery, and this can be anywhere from outcrop scales, where we might use drones, to actually having high resolution imagery of thin sections where we can actually zoom in at very high magnification, to having simple gigapans of outcrop exposures, stitching them together, and having a wide variety of choices of data, even if we can't physically get to the outcrop. So in this particular case, taking an example from, again, southeastern Utah, there are some beautiful examples of exposed and exhumed channels. So all the fine-grained material around has eroded away, so that the resistant channel sandstones are left. And kind of looking at this particular area, be able to show you an example of the Cretaceous Cedar Mountain. This would be a digital model composed of about 500 images. It took a lot of processing. This was put together by Casey Duncan, and you can get an idea of some of the resolution of this particular model. And so this could be something that is used for teaching, even if you can't access it or even get up to some of the small cliff faces of the outcrop. So I'll show this little model here. And you can see the exhumed fluvial channels. This is zooming in, and you can see the contact of the channel overlying some of the floodplain deposits. You can see some of the relative heights and the change of the bedding, interior or internal bedding, and the change in some of the cross bed thicknesses. And you can kind of look at some of the lateral changes as you move along to the sides of the outcrop. Maybe going around the corner here. And kind of going in zooming in to take a closer look at the contact. You'll be able to see the sharpness of the contact and some of these pebble lags and some of the coarse grained material comprising the area right at the bottom. So these are great examples of what can be done in the future. Okay, now the case of the missing marbles. This is the second example that I wanted to talk about to demonstrate how we as scientists can make contributions to protecting some of our resources. These are examples of iron oxide concretions that I've studied for a number of years. This is in the area of Grand Staircase Escalante National Monument in southern Utah. And here we have unusual preservation of these cemented mineral masses. And these are more resistant to weathering, so they typically accumulate as these lags. And these are unusual in part because of the golf ball size. So these concretions are cemented mineral masses. They're preferentially cemented in sandstone. These are important indicators of past fluid flow conditions. They're actually a physical mineral record of fluids that deposited that cement. The Jurassic Navajo sandstone is a classic example of a unit that has a lot of these iron oxide concretions, maybe in part because it's one of the most porous units on the Colorado Plateau and was a preferential flow path for many different fluids. You can see that there's other compositions of concretions that can also occur in the geologic record. These might include malachite examples shown in green and azurite examples shown in blue. These concretionary forms are significant diagenetic records, we said, of fluid flow. And they're important because we can use these terrestrial examples to compare to Mars. And in 2004, the rover Opportunity took some of these pictures. You can see that this has false color superimposed, but the hematite spherules that were discovered are shown in false color of yellow so that they actually stand out. And you can see that these have a dispersed distribution, so they're physically not touching each other, much the way we have these examples here on Earth. And these are telling us about saturated conditions of groundwater. And these particular hematite spherules were analyzed to verify the hematite composition. If you could see them with your naked eye, they might look like this, where they might have kind of a steel blue color. And because of the way they look and maybe their distribution, these are called blueberries. And so these might even be like blueberries in a muffin in their physical distribution. And so you can see the similarity to some of these examples in Utah. Now, in 2012, the BLM law enforcement was investigating theft, transportation, and sale of some of these concretions that are locally known as Moki marbles. And there were 3 suspects in that case. In 2015, 2 suspects were also caught stealing marbles, and one of them had been previously involved in the 2012 investigation. You can see the before pictures on the left and the after pictures on the right. You can see how disturbed the area was after somebody went in with a bulldozer and you can, a front end loader, and you can see some of the tire marks that are shown here. And they actually scooped up some of the marbles and took them away for sale. But BLM needed proof that the marbles were from Grand Staircase. And you can see that the before and after images were sobering. They had piled these up and maybe left some of the remnants that they didn't think were as saleable. And it was quite striking, the difference. BLM stored some of the stolen goods in a warehouse. In 2012, they had 64 of these 5-gallon buckets filled with marbles. In 2015, they confiscated another 39 buckets. So over 100 buckets of these marbles. And in each bucket, there were over 300 marbles. So we had estimated a total of over 42,000 marbles that were stolen off of federal land. And because these often sell on eBay or at gem and mineral shows and such, we could estimate that the value was over $300,000. So what was the proof that these were actually from the Grand Staircase Escalante federal lands that BLM was managing? Well, we had these different criteria, and from our scientific studies, we knew that the size was distinctive. There weren't other places where you had those golf ball sizes in large quantities. We had these nearly spherical shapes, as well as some that looked like flying saucers. And typically those flying saucers had these ridges along the Aeolian lamina of the Jurassic Navajo sandstone. Some had a very distinctive outer skin that was either smooth, or some were a little bit bumpy, like avocado skin. There was a distinctive kind of patina, and there was some internal structure showing the rinds like this. You can see the sample, our scientific sample on the right, and the BLM cut sample on the left. And we could see that they had these poorly cemented cores, and the distinctive mineralogy of the rind is goethite, F-E-O-O-H. So there was enough evidence that we could say these were indeed from Grand Staircase. There were felony charges against the 4 individuals who had stolen the marbles. They all pled guilty. Here are the defendants just assigned a number. Only one got a prison term, and all of them did get some supervised release. You can see some of the fines, and the largest fine went to the person that was a rock or a gem dealer. The future of the marbles is that they will likely be returned to the setting, possibly with a sign. Some have already gone into visitor centers, museums, different teaching programs, and for education, and some on display. This was a unique case for BLM because the marbles actually had a specific value. Over time, you can see that this wasn't an investigation that went very quickly. There was actually 2 years of investigation, and then actually 3 years of litigation before everything was resolved. So how can we help with cases like this? This is where we can actually use technology, and this technology is really going to take us well into the future. We've already seen how we use drones and maybe high resolution imagery to document changes that might occur on the landscape. We also have the capability of sharing information through social media, and through social media we can actually share more information and raise awareness. And here's an example of an app, Terra Truth, and this is where you can actually report damage on some public lands. In this case, for the state of Utah, users can report damage to Utah's public lands. They could report if they think Moki marbles are stolen, or if there's outcrop damage, maybe there's stolen rock art, or things have been defaced, or even perhaps oil spills. And so this kind of technology is taking us into the future and allowing us to do things that we weren't quite able to do quite as easily in the past. There are changes in the wind. In the old days, we used to be like this, recording all of our field information, handwriting it down in our field notebook. But now the new generation is like this on the right. We have an increasing number of women, and we're incorporating digital technology in the field. The National Science Foundation recognized that we had the opportunity to advance the science and meet some of the grand challenges by using cyber technology. And so they came up with an initiative that's called EarthCube. And EarthCube is actually designed to help our scientists make some small test programs to actually show how the technology can be applied for our science. Geologists are a little difficult. I view myself as one of these Luddites who has a hard time adapting, and we have such personalized and descriptive data that's very complex and multidimensional, and so much of especially sedimentary geology is interpretive. So I've written an article about this. Although we do have difficulties and challenges, it is possible to overcome those, and there is a great future in sharing data openly and using the cyber technology for earth science. One example of a great program is ROCD, and this is a program that was run through a grant by Shannon Peters at the University of Wisconsin. And this particular program uses your GPS locality on your mobile device. You can actually use your GPS to see what the geology is, and that can pull up a geologic map, as well as actually tell you some of the stratigraphy based on your locality. So some of the other types of things that are being sponsored, have been sponsored by EarthCube, is an application called Strobospot. This is a field geology tablet app that was originally designed for structured tectonics, but we've actually just started applying this to sedimentary geology. So this is our new field assistant that allows us to collect field data. We can actually build stratigraphic columns in the field. But most importantly, we might eventually be able to have this back-end data management system where all of our collected field data would go into this database, and we would be able to call up localities. Where did I sample concretions? Show me all the locations that have concretions, or show me all the locations that have this particular fossil, etc. Or show me all the studies that have been done at a particular field outcrop. So there's an exciting future. We have students actually measuring strike and dip using their mobile apps. There still may be some challenges seeing the screen in the field, but some of these things are likely to change. These are some examples of a basic stratigraphic column. It might not be quite publication ready, but really this is designed mostly to collect the data as opposed to just generating something for publication. We can actually link some of these different beds to the outcrop, and we could even tie in individual photos, link those to the individual beds where we collected or where we took those photos. So there is the possibility of having all of these multiple scales of data that are integrated and put into these database management systems. We could also possibly display these in a GIS type of platform. So NASA did this for some of the Mars data. They also have done it for the moon. You don't have quite as much data on these planetary bodies, but you can use this much like Google Earth. You can go in and zoom. You could perhaps look at different data from some of the different Mars missions, and in particular, you might be able to analyze between different data sets. Here you can see some of the highest resolution satellite imagery at 25 centimeters per pixel. You can look at some of the beautiful types of landforms that you can see. You could actually even do some calculations. You could select a line and actually instantaneously generate a elevational cross topographic profile, and maybe eventually we'd be able to do something like cross sections. You could find out the locations of the current orbiter. You can easily span across different terrains, and you can select an area and even print it out on a 3D printer. You could display bookmarks. You could actually show some of the areas of where, let's say, the rover is going and what kind of data it's collecting at different times, at different sols. You could actually even look at some of the changes of some of the sites that we might use in popular culture through science fiction, or in this case, from the movie The Martian. You can actually explore the path that Mark Watney might have had to take in order to get rescued. His path through Marth Vallis and maybe some of the areas of deep craters and such. So you have this opportunity to actually mix different types of data between science and culture, popular culture, and just general interest. So in conclusion, I would like to say that cyber technology and science is a hot area. It's a hot area for the future, and it's going to allow our science to make new integrations, discoveries. It'll help us visualize our data, and it will aid in us networking, maybe even across different disciplines. It really is an exciting future that is ahead. So to summarize, we have an ethical responsibility to our science to actually conserve and preserve important geoheritage sites. We need to leverage some of the new technology to help us conserve our heritage. And in particular, some of the new technology in terms of digital imagery and models is exciting. The future, we can actually find more opportunities to be proactive. We can continue education about geoheritage and about geoconservation. The future is exciting, and I want to say that there are many frontiers for those that want to explore more about Earth, as well as even other planets. I think in particular, as we think about where our science is going in the future, the most diverse teams might be able to actually help us find the best science. Protect Earth and explore new worlds. Thank you for joining me today.